All right, so the next thing we're going to do is switch gears a little bit, and we're going to sort of finish off our discussion of significant figures. In a couple of the previous videos, we talked about recognizing significant figures in a particular measurement. We saw that every non-zero digit is always significant, and then we looked at zeros. Confined zeros, always significant. Zeros at the front of a number, leading zeros are not significant. And then zeros at the end of a number are only significant if there's a decimal point in the number. So now we're going to take a look at applying some of that information to calculations and significant figures. Now, we're not going to go into this into a whole lot of detail, but the point of this class is not really to get into the minutia about sig figs, but we still need to address a little bit about significant figures, especially when we do some basic calculations. We need to make sure that we still are able to keep that in our measurement. So when it comes to significant figures and calculations, there are two rules that we're going to see. Okay, and the rules depend on the mathematical operations that you're doing to the number. So the first rule applies to multiplication and division. Okay, and the rule says that the answer, when you multiply and or divide numbers, the answer can only have as many significant figure, only has as many sig figs, I'll abbreviate that as SF, as the number with the least number of significant figures, number with the least number of significant figures. So for example, if I have 1.0 and I multiply that by 5.0000000, and let's just put in some units here so we keep track of that. Well, then this number here, right, that has 2 sig figs. This number here has 1, 2, 3, 4, 5, 6, 7 significant figures. So according to this rule, whatever answer I get can only have 2 significant figures because that's the number with the least number of sig figs. So obviously 5 times 1 is 5, but this has to have 2 significant figures. I need to add that 0.0 there at the end, right? So this has 2 sig figs. That's the rule. For multiplication, it's the same rule for division. Okay, so what we're doing here is we're looking at the number with the least number of sig figs, and then that's the number of sig figs you want to round your final answer to when you perform the operation. Okay, let's take a look at another example. Let's say I have 3.92 meters times 2.756 meters, and I'm going to divide that by 1.2 seconds. Okay, so when you stick that in your calculator, and again, your calculator is only going to do what you tell it to do. It doesn't round things for you to the correct number of sig figs. You need to round it by applying the rules. So here, if I plug all 3 of those numbers into my calculator, what do I get? Well, I have 3.92 times 2.7560, and I get a number. I'm just going to divide it by 1.2 right away, and then I'm just going to write out what the calculator tells me. So it tells me 9.00293333, repeating. Okay, that's what I get. This is my calculator answer. That is not your final answer. You need to round that to the correct number of sig figs. Now, before we get to the correct number of sig figs, let's take a look at the units, right? So here I have meter times meter. That gives me meters squared. And then I have seconds in the denominator, so that's a meter squared per second. Those are my units, right? Those are derived units that I get because nothing cancels out here, right? The meter times the meter divided by seconds, meter squared per second. So according to the rule I mentioned above, I'm going to look at my number of sig figs. 3.92 has 3 sig figs. Okay, 2.7560 has 1, 2, 3, 4, 5 sig figs. And then 1.2 has 2 sig figs. So this means my final answer then needs to be rounded. We'll round this to 2 significant figures. Okay, so I go, let me highlight the first 2 sig figs. So the 9 and the 0 here, significant. The next digit obviously is a 0, so I'm going to keep the previous digit as it is. So this becomes 9.0. From a 0 at the end of a number with a decimal point, a significant, and then my units, meter squared per second. Okay, that's the rule for multiplication. Same rule for division. When you're dealing with these measured numbers, right? Numbers that have some degree of uncertainty associated with them. Okay, that's the rule for multiplication division. What about the second rule that is going to apply to, so this applies to addition and also the same rule for subtraction. So according to this rule, it says that the answer only have as many decimal places as the number, the least number of decimal places. So in other words, okay, we're not looking at sig figs in this case. What we're looking at here is the precision of the measurements themselves. And when we add, subtract, we can only be as precise as the number or the measurement with the least precision, the least number of decimal places. So for example, if I add together the following, let's say I have 3.92 meters plus 1.007 meters plus, let's say 2.1 meters. Okay, so if I add those together, and what I find sort of a good strategy to do here would be to rewrite my numbers, and I just line up the decimals. So 3.92, 1.007, and then 2.1. I'm going to add these together, and you can do it in your head. You can use your calculator, it doesn't matter. So 3.92 plus 1.007 plus 2.1, and that's going to give me 7.027. Okay, this is my calculator answer. That is not your final answer. You need to interpret it in terms of significant figures. So I'm going to look at my numbers, see which number has the least numbers. I'm sorry, least number of decimal places. That obviously is the last one. That is this one down here. And I'm just going to draw a line right after that second or the first decimal place. And I'm just going to extend the line all the way down to my answer as well. So now I need to round my final answer to now that first decimal place. The next digit, the 2, is less than 5. So then this becomes 7.0 meters. Right? So I've rounded this now to 1 decimal place because this number here has the least number of decimal places, which is 1 decimal place. Okay, so that's the rule. Now, in some cases, you might be presented with numbers that don't have decimal places. So what do we do in those cases? Well, let's take a look. Let's say I added together 330 meters plus let's say 432 meters plus 100 meters. Right here, you don't see any decimal places, but we can again rewrite these. So we have 330 we have 432, and then we have 100 meters, right? And these are all measurements because we're measuring lengths in this case. Now the M here is an abbreviation for meters. So if you stick this in your calculator, what do we get? 2, 3, and 3, 6, 4, 5, and 3 is 8 meters, right? This is your calculator answer. But according to the rule above, it says answer can only have as many decimal places as the least number of decimal places. Another way of stating this is that the answer can only be could be as precise as the least precise measurement. So in this case, we don't have any decimal places, but we can look at the precision of these measurements, right? So according to all the rules you talked about identifying 6 things before, this first measurement here, we could estimate it to the tens place, which is the 3. The second measurement, we could estimate it to the ones place, which is the 2. Whereas the third measurement, we could only estimate this to the hundreds place. So according to so we don't have any decimal places, but we can still look at the precision. This one here is the least precise. Okay, because this is estimated to the hundreds place. Which means my final answer, I can also only estimate to the hundredths place, right? So this, even though there isn't a decimal place, based on the precision, this here is the place at which I need to estimate my final answer to. So look at the next digit, 5 or above, I'm gonna round this up. So this becomes 9. I replace the remaining digit with 0. So this becomes 900 meters as my rounded answer, according to the rules for sig figs. Okay, so this is and you'll run into situations like these. There'll probably be a few on your next quiz, for example. You don't have any decimal places, but you're still applying the same general rule, which is the answer can only be as precise as the least precise measurement. Just as in the case of the ones with the decimal, the 2.1 here, this is the least precise measurement, right? You can only estimate this to the tenths place. The first one you could estimate to the hundredths. This one you could estimate to the thousandths. That means your final answer can only estimate to the tenths. It's the same idea, except now you're on the other side of the decimal point with your measurement. Okay, so 2 different rules. One for addition, subtraction. You look at the least precise measurement. One for multiplication, division, where you look at the number of sig figs. Which again, all the rules here still fall under the same umbrella, right? Which is that the final answer really can only be as precise as the least precise measurement. Similarly here, right, we're multiplying 2 sig figs by 7 sig figs. This first one can only estimate to in this case, the tenths place with the 2 sig figs. So then the final answer can only have 2 sig figs as well. The key thing here is you don't want to confuse your rules. So don't use one rule in one place when you should have used it in a different place, because that's maybe the most common example, the most common place where students make that mistake.